So I made it 50. I made it 5 kilograms, so the weight is 50 newtons, because I put it on Earth 2. Sine of 53 degrees is about 0.8, so 8 times 40, so that is indeed 40 there. That would be 80. That's 20. I can divide by 20, so I have x squared minus 2x minus 4 equals 0. That's much easier to work with. Do we have any confirmation of any of that stuff?
I redid it, and I got the same thing.
And you got what?
I got the same things.
As Ryan?
Yes.
This right here? Okay. All right, so we have two answers there. We have 3.236 and negative 1.236. What are the units?
Meters.
Which of these is the correct answer? And what does the other one mean?
The 3.236.
Okay. That is indeed the correct answer. What is the meaning of the negative 1.236 meters? It does have physical meaning.
Other than the fact that it's a parabola with 2 points.
Other than that.
Is that? So if the spring gets compressed, it probably pushes back, correct?
Right?
So is that how far it pushes the box back? Or is that how far the spring goes back after the box stops?
You're sort of on the right track. I don't know if it's what you intended. The way you worded it was a little bit off. At least what I heard was a little bit off, but it's possible you intended the correct answer. If the box stuck to the spring, that's how far the spring would extend past what its initial position was. So if the box stuck to the spring, it would then expand, and whatever its starting point was, it would go 1.236 meters past that, with the box still attached. So that would be the physical meaning. So there could be a part B to the question of, how much did it compress? If the box magically stuck to the spring, how far out would, how much beyond its initial spring position would the spring now stretch? All right, questions to hear? All right. I promised you friction, so we gotta do some friction. So we're gonna do a similar problem, except this time, I've got my mat, I've got my ramp here, I've got my 5 kilogram mass, I've got my 53-degree angle, got my spring, and this has friction. UK is equal to just 0.3, why not? This is 2 meters. And now the question is, how much will the spring compress? So when we do the force diagram, looking at the forces, we do have an additional force here. Weight is acting down, of course. Normal force perpendicular to the ramp. The spring is going to, the elastic force is going to, or spring force is going to be up the ramp, and friction will be up the ramp as well. It is kinetic friction because we know the box is sliding. From an energy point of view, it starts out with all this potential energy, no kinetic energy. As it goes down the ramp, the potential energy will decrease, the kinetic energy will increase. It'll hit some maximum point, at which point it'll start to slow down. Kinetic energy will decrease as the potential, now elastic potential, will increase. With friction, we're losing energy. We have a certain amount of energy we can play with, and friction is just taking it away from us. I know that the work done by a non-conservative force is equal to the change in energy. Change always final minus initial. If I add the initial energy over to the other side, I have my initial energy plus the non-conservative work is equal to my final energy. Similar to what we had with the problem we just did, except in the previous problem there was no non-conservative work being done, so we started with EI equals EF. Now we've got this conservative, non-conservative work. 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared plus the non-conservative work, which is, well, the box is going down the ramp, the friction is acting up the ramp, so that work is going to be negative, plus negative friction times x equals 1/2 mv final squared plus mgh final plus 1/2 k x final squared. I guess that really should be x final. Because this box is going to come down, hit the spring is going to compress some distance x. And that's also, so that's how much the spring compresses, that's also how much, how long, or the distance through which the friction is acting. We do need to break weight up, but it's a simple enough breakup. So I have W cosine theta into the ramp, W sine theta down the ramp. Normal force, the elastic spring force, friction force. And the reason I do that is I do need to know the normal force as friction is involved here. All right, we can go through and figure out what's zero. I am going to amend something that Ethan put H is equal to 0 at the very end of the compression. I'm just going to put it in a different spot this time. I want to put H is equal to 0 here. Still end up in the same answer, just there's some subtle differences that I think is worth showing.
The initial speed. Delta X initial.
Final velocity.
What else?
Final speed.
And that's it. Now, it might seem more complicated because we have two more terms than we had last time. But in some ways, I mentally find this simpler. So we have mg times the initial height. So mg times the initial height. Well, the initial height is just 2 sine theta. Because my initial height is that distance. That's my hypotenuse. This is my initial height. Minus my friction force, which is mu k, times y, times how far the spring compresses, which I established as x, equals mgh final, which is mg. Well, my final height, again, it's the hypotenuse times the sine of theta. My hypotenuse is x. My final height would that be x sine theta. But we need to take into account that we are below our initial height. So times negative x sine theta plus mgh, no, that was mgh final, and then 1/2 k x squared. The advantage of picking this is I'm not squaring a binomial. We cut out that part of it. It depends on where you want to put the math. Plugging in numbers, I know m is 5, g is 10, sine of theta is about 0.8. So this becomes 80 minus y is mg cosine theta. That's about 0.6, that's 50, so this should be 30 times mu k, which we established somewhere as 0.3, there it is. So that is 9x equals 50 times sine of theta, which is 40, so negative 40x. And then 1/2 kx squared, k was 40, so that's 20 plus 20x squared. That's the math problem. If there were no friction, that would disappear, and we end up with an equation that we had on the previous page. Put it in quadratic form, 20, or standard form, 20x squared minus over 31x minus 80 equals 0. Minus sign. And plug and chug again. So x is going to be equal to 31 plus or minus the square root of 31 squared minus 4 times 20 times negative 80 divided by 2 times 20. We will get two answers. One of them is correct.
Negative 2.253.
You get 2.253.
Negative, yeah.
You got negative
Yeah, and then 17.753.
17.75. I will contend that this cannot be right. Or we made a mistake on the other one. The maximum compression should be less than what we had last time. Because this number is smaller than before. What's under the radical should be smaller than what we had before. So we should get a number smaller than what we had before.
I got 2.89
That would make more sense. And
and negative 1.39.
all right, the 2.89 meters would be, of those two, would be the answer that makes sense. Other number really loses physical meaning because we have lost energy with friction. So if the mass compresses, it lost that energy, and then as it moves back up, if I still have friction, it's losing more energy. So it will not actually go that far if the box sticks to it, because we're gonna be losing more energy. It won't go beyond that 1.39 meters past its initial spring position if the box is stuck. Anyway, energy, friction, I think what most people will call it a good time. That's right, you got one person back there nodding yes. And other people giving me that look that I've done it several times. Yeah, I'm talking about you, Kelly.
Are these the new concepts for the next chapters?
This is primarily an energy thing. This is an energy thing, which is not on the testimony. Please.
I feel that same way too, I just,
Okay, they express it for both of you?
yeah, I'm just,
That's probably why it was a little bit exaggerated there.
yeah, it's more expressive.
All right. So, I guess test tomorrow, we got Thursday. We're gonna look at some of the same stuff we've been doing, except this time with momentum.
Yay.
That's right, that's the right response. I would also accept woohoo, except with more enthusiasm, the Louise kind of way that you would say woohoo. Woohoo! Maybe arms sort of up in the air, like you're on a roller coaster. I will expect that you will work on your enthusiastic responses, and then on Thursday, we will all be overwhelmed with the enthusiasm. All right. Have a wonderful day.